Hey there, and welcome. Today, we are diving into two of the secret ingredients for some seriously powerful functional programming in Rust: closures and higher-order functions. These are the tools that let you build super elegant, reusable code, which is absolutely critical when you're building high-performance systems like Solana. This explainer was made by Forge College, so let's get right into it.
So let's just jump right in with a question that really gets to the core of what we're talking about today. Have you ever been coding along and just thought, man, I really wish I had a function that could, remember stuff from the world around it?
Well, you are in luck, because this explainer is going to show you exactly how to do that. First, we're going to unpack what these functions with a memory actually are. Then we'll get into their 3 different flavors for capturing variables. After that, we'll see how to use them as ingredients inside other functions. And we'll even build our own little data pipeline. And finally, we'll wrap it all up with the key things you'll want to take away from this.
All right, let's get started. Section 1. Let's unpack this idea of a recipe card for functions that can remember.
So here's the deal. A closure isn't your average function. It's what we call an anonymous function. And its superpower is that it can remember and use things from its environment. The best way to think about it is like a recipe card. But it's a magic recipe card that not only has the instructions, but it also knows what ingredients you already have sitting in your kitchen. It captures that context from around it.
But how does it actually remember or capture those variables? This is where things get really cool, because Rust doesn't just give us one way to do this. It gives us 3 distinct ways, or as I like to call them, flavors, for a closure to interact with its environment.
To get this, just picture it like this. Your main function is this big box, right? That's the environment, and it's got some variables inside. Now, the closure is a little box inside that needs to reach out and use one of those variables. That act of reaching out and grabbing the variable, that's the essence of capturing.
And here's where Rust gets really clever. It automatically figures out how the closure needs to capture the variable, and it categorizes it into one of 3 special traits. If it only needs to read the data, it's Fn, an immutable borrow. If it needs to change the data, it becomes FnMut, a mutable borrow. And if it needs to take the data and run away with it, it's FnOnce. It takes ownership completely. Let's give them some personality so this really sticks. First up, you have Fn. Think of Fn as the polite guest at a party. It'll happily look at your photo albums, but it won't draw mustaches on the pictures. It's just there to read the data. Then you've got FMut. This is your helpful friend who comes over and says, hey, your spice rack is a mess. Let me alphabetize it for you. It can actually change the data it borrows. It's there to help out and make modifications. And finally, FnOnce. FnOnce is the cookie monster. It sees that last cookie on the plate, it takes it, and it eats it. It's gone forever. It takes complete ownership of the variable, which means it can only be called once. Makes sense, right? You can't eat the same cookie twice.
Okay, so now we have these special recipe cards, our closures. That's great, but we need a master chef who knows how to use them, right?
And that is where higher-order functions come into play. Now, it's a fancy-sounding name, I know, but the idea is actually super simple and incredibly powerful. A higher-order function is just a function that treats other functions like ingredients. It can either take a function as an argument, or it can cook something up and return a brand new function as its result.
For instance, let's whip up a couple of simple ingredient closures right here in Rust. We've got add, which takes a number and just adds 3 to it. Simple enough. And we have multiply, which takes a number and doubles it. These are our basic little building blocks.
So, how do we combine these little building blocks? Well, we're going to use a higher-order function to build our own reusable pipeline with these ingredients. This is where the magic really starts to happen.
Check this out. We're going to write a function called compose, and this is our master chef. Look at what it does. It takes 2 functions, f and g, and it returns a brand new function. And that new function knows to run f first and then run g on whatever comes out of f. That whole where clause at the bottom, that's just Rust's way of making sure the pipes fit together, that the output of the first function matches the input of the second. It's a generic recipe for snapping any 2 steps together.
And look at how beautifully this works in practice. We take our add and multiply closures and we pass them into compose. Out comes a totally new closure that we're calling pipeline. Now, when we give pipeline the number 4, what happens? It first runs add on it, turning 4 into 7. Then it immediately runs multiply on that 7, giving us our final answer of 14. How cool is that? We just built a custom data processing pipeline in 3 little lines.
All right, your turn. I really encourage you to pause here and try this, because it's the best way to make these concepts stick. It's a quick 3-step workout. First, write a simple closure that captures some variable. Second, use that compose function we just built to link 2 of your own closures together. And third, try writing a function that actually accepts a closure as one of its arguments. Give it a shot.
Okay, awesome job. Let's zoom out for a second and really lock in the most important things to remember from all of this.
So here's the recap. The big idea is that closures are basically functions with memory. And depending on how they use that memory, REST automatically picks Fn, FmUt, or FnOnce for them. The whole point of this is to compose these small, focused closures to build these amazing reusable pipelines. Now, when you pass them in the functions, you've got 2 main choices, using generics for raw speed or using something called a box when you need more flexibility. Let's quickly look at what that really means.
This is a really crucial choice you'll make all the time. On one hand, you can use generic trait bounds. This is when the compiler creates a specialized, super fast version of your function for every single closure you give it. We call that static dispatch. It's fast. On the other hand, you can use a boxed trait object. Think of this like a generic toolbox that can hold any kind of closure, which is super flexible, but it comes with a tiny performance cost at runtime. That's dynamic dispatch. Speed versus flexibility.
You know, getting a handle on closures and higher-order functions is a massive step forward. It really sets you up for the next big question, which is, what if you could take this idea of creating abstract recipes for behavior and apply it not just to little anonymous functions, but to entire data structures?
And that, my friends, is a little teaser for Rust's powerful trait system, which is a concept you are going to use constantly when you're building hyper-efficient programs on platforms like Solana. But we'll save that for next time. This explainer was made by Forge College. If you want to dive deeper into Rust for Solana development and other key Web3 topics, make sure you visit us at forge.college. Thanks so much for watching.